Hello again everyone, welcome back to ptet.chemistry channel. So this is a 7th out of 10 video on these infographics that have been provided by Cambridge International during the COVID pandemic on their Resource Plus website. So a PDF copy of this infographic can be obtained from the Google Drive link in the video description below. So this is by no means a complete overview of your A-level specification or syllabus. For that, you have to refer back to your own curriculum document, okay? So what this does is it helps you to see the topic connections, and along the way, I'll highlight to you what are the kind of things that you can find on my playlist on my channel, and hopefully this should help you to navigate around. But if you're just looking for tutorials on certain topics, this is not a video for you. Please navigate to the other videos, other playlists on my channel to find what you're looking for, okay? So this is talking about electricity and metals. As we know, from GCSE or O-level, we talk about extraction of metal, which of course you can use reduction with carbon. That will be the cheaper method, but not all metal can be extracted that way, and we have to resort to electrolysis, which involve a large amount of electricity, both of which still involve redox changes, and therefore this is where we talk about these redox changes and the generation of electrode potentials that results in whether you're using electricity or in the case of generating electricity from reactions that have a certain standard cell potential, all right? So the idea of electrolysis revolves around this thing called Faraday constant, the value of which is 96,000 something, 96,500 if I'm not mistaken, right? So you can have a look at your data booklet. It's the charge that 1 mole of electron will carry, coulomb per mole. And then the charge of 1 electron is 1.602 times 10 to the minus 19. The relative sign is of course negative, okay? But then you have 1 mole of electrons, which is Avogadro constant. So Avogadro constant times the charge of 1 electron will give you 96,500 coulomb per mole, not taking into account, so basically ignoring the negative sign there. Cathode attracts cations. Cations are positively charged, so attracts cations. Cations are positively charged. That makes your cathode negative, all right? So we talk about red cat. So reduction would happen at the cathode, okay? To favor reduction, you need or you want the most positive E naught. Okay, when you compare metal cations versus H plus, what are they talking about? They have totally gotten this the other way around. The metal or the H2 would be at the cathode, and the halogen and the O2 would be at the anode, okay? They've totally got it the other way around, okay? So when you look at the metal cations and H plus, the H plus 2 electrons going to H2. That by default is your standard hydrogen electrode. Is 0.00 volt. And most metals, reactive metal cations, the E naught will be negative. Because this is more positive, this will be favoring reduction at the cathode. That's why you generally release H2 at the cathode instead of the metal, unless you have a metal which has an E naught which is less positive than the H2. Things such as copper, silver, and gold, they have a more positive E naught than the standard hydrogen electron, 0.00. So they will be displaced at the cathode. For the anode, the same thing, but we want the more negative E naught will be displaced at the anode. These are the things you don't cover in GCSE and O-level, and these things become very clearly identified in your A2 electrochemistry, where you deal with these more advanced concepts of E naught, you can check my topical playlist on A2 electrochemistry to understand calculation involving this thing, which always crop up again and again. Students tend to get confused between the unit bookkeeping and the type of calculations to understand what is going on, all right? As well as further details on this. This is basically what I mentioned just now. The more positive it is, the more it favor reduction, because the more it favor reduction means it favor this reaction going from left to right. That means these things likes to be reduced, and therefore it is more oxidizing. An oxidizing agent oxidizes the other substance, itself is reduced. The more you like to be reduced, the better you are as an oxidizing agent, and the reverse is true. Okay, this is Nernst equation. This is standard reduction potential from your data booklet, assuming standard condition of 1.00 mole per dm cube. When your concentration changes and are no longer under standard conditions, then you need to use Nernst equation to work out the electrode potential under non-standard condition as related to the electrode potential under standard condition, also known as standard electrode potential. Okay, they have this thing where it's plus blah 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 blah, oxidize and reduce. So when you talk about which one is which one, this thing gains electron. Okay, so this thing is called the reduced species. It is what you get after you undergo reduction. Okay, this is what you get after you undergo oxidation. So if you look at data booklet, all of them are shown as reduction potential. So that means the oxidized over the reduced species is the left hand side over the right hand side, assuming you have set them up as reduction potential equilibrium. Okay, they relate this to transition metals. I don't know why, but because they put electrolysis and metals here, I guess you can talk about transition metals, definitions, physical properties, chemical properties. The first raw or transition elements are essentially your whole A-level transition metal chemistry, although specifically in the syllabus they mention copper and cobalt chemistry. Okay, but that doesn't mean they cannot ask you anything else. All right, definition of ligands. We talk about dative covalent bond. Very, very important that you can differentiate what is dative covalent bond. And we talk about ligands. We talk about denticity, so bidentate, polydentate, etc., etc. We talk about coordination number. Okay, we talk about shape, or we talk about geometry. We talk about isomerism. So these are all stuff which are commonly asked about transition metal chemistry in A level, and they can also relate it to redox chemistry. I guess that's how they put them together. All right, and you can find out more of these in the A-level topical playlist on transition metals. Make sure you don't choose the O-level transition metals, because they will be extremely simple. As you know, if you're doing A-level, you should be looking at A-level transition metal kind of chemistry. Okay, the next bit is on battery and fuel cell. We talk about clean energy, where you have a perpetual or a continuous system that keep on generating you the H2 and O2 that gives you the H2O, and that equation is not balanced. I don't like that. Okay, I mean, Cambridge always asks you to write balance equation, but they themselves didn't write the balance equation in this infographic, and that's quite bad. Okay, the whole idea is that you only generate H2O, unlike combustion of fossil fuels, which give you energy. Okay, when they combust the fossil fuel, they also give CO2, which is a greenhouse gas and can cause global warming. But here is just hydrogen combusting oxygen. Clean, very clean, just produce water. And then the H2O gets electrolyzed again in the presence of a catalyst to give you back hydrogen and oxygen, and so on and so forth. Okay. Just now we talked about the chemical properties of transition elements, but this bit is also on the physical property of transition element. You should know how to draw the 5 sets of the d orbitals. They get split in the presence of ligand. So such as the octahedral ligand field. So they get split into a set of 3 and 2. they are separated by this energy gap, delta E, equal to the Planck constant, H, times the frequency of the electromagnetic radiation. Because if you have electrons in a low energy level, you can absorb energy by absorbing visible light, photons, okay? But you have to absorb in the correct wavelength, because visible light is electromagnetic radiation. If you have done GCSE or O-level physics, speed of light equal to frequency times wavelength, because electromagnetic radiation, they all travel at the speed of light. So rearranging the equation, you will get the energy gap is related to Planck constant times speed of light, which are constant times constant. The bottom bit is what is changing. So your energy gap is governed by what wavelength of the visible light is being absorbed, and whatever is being absorbed, your electron will get excited, or what we say promoted, from a low energy level to the higher energy level. Okay, and this contribute to colors. Okay, in a tetrahedral field, is the other way, splitting around. Okay, but essentially they do get split in the presence of ligand, and you can only get promoted and absorb visible light if you have empty orbital. That means things that are D10, where you have 1, 2, 3, 4, 5, 6, 7, 9, 8, 10, where you are completely filled, D10. Things such as gold 1, copper 1, I don't know, mercury 2, etc. So they all will have D10 electronic configuration. If you don't know how to work out electronic configuration of atom and ions, I suggest you have a look at my topical playlist on atomic structure. That is in AS chemistry playlist. Okay, atomic structure. And then work out the D10 configuration. Everything is filled. So that means even if you can absorb visible light in this energy gap, but there's nowhere for you to go because it's completely filled. So there's nowhere for you to go, therefore you can't do any absorption of visible light. Okay, even though you have supply with visible light, that means you're not absorbing anything because you can't get promoted into something that is completely filled already. Things such as this configuration. So you don't get any colors. That's why complexes, transition metal complexes, featuring these particular cations, amongst many other examples, they are colorless, whereas these things are colored because you got empty orbitals. You have splitting, you can absorb visible light, and what color you see depends on whatever is being absorbed. So you see the combination of the visible light that is not being absorbed. This is called complementary. The color that you see is complementary of the color that is being absorbed. The colors of your case studies are very important, especially for copper chemistry and cobalt chemistry, that have been specifically outlined in the specification and syllabus. I guess one of the most important reactions in A-level transition metal chemistry is talking about ligand substitution reaction. So that is a pale blue solution. When you add a bit of ammonia, initially you get a acid-base reaction. You get a precipitation reaction. That is in a small amount of aqueous ammonia, as you will have known this from your GCSE and also O-level doing practical chemistry. Okay, so when you add ammonia, you can get copper with 2 hydroxide. Essentially, you can also talk about 4H2O remaining, but there's no charge. I'll probably, instead of using NH3, I'll talk about it using 2OH minus, and then you will get just balancing the equation now, 2H2O. Some books will show it without the 4H2O, so that means you kick out 6H2O. That's perfectly fine. This is a precipitation reaction because this is aqueous, this is aqueous, this is solid, this is liquid. That is a pale blue precipitate or solid. Okay, but again, this is because NH3 is a weak base. It dissociates in water to give you OH minus. partially, because it's a weak base. It partially ionizes in water to give you OH minus. This could happen first. But then NH3 can also act as a ligand because you have a lone pair on the ammonia, on the nitrogen, okay? So it can do a ligand substitution reaction in the excess of ammonia. And after that, this pale blue precipitate will dissolve to give you a dark blue solution. If you have done practical chemistry, you must have seen this. You got to have seen this because it's also quite a popular question in A-level paper 3 practical. And there's no way you can do A-level chemistry without doing practical, whereas you could opt for alternative to practical in O-level or GCSE. All right. We talk about this thing called K step. It's a stability constant. It is a form of equilibrium constant. Okay. You note that the water have not been included in stability constant because it's not exactly Kc, it's K step. So it's already taken into account the water concentration is so big that it's roughly constant. You can see examples of this in the transition metal chemistry topical playlist, where they like to ask questions like this. As a matter of fact, I don't like the 2 plus there. I like the 2 plus there because it doesn't belong to the water, it belongs to the copper. But the other thing is, once you put a 2 plus there, it's no longer a concentration. This square bracket represents how you write transition metal complex. Put another big square bracket outside, okay? So that way, you can do it much better. This is wrong. Cambridge has done so many wrong things, okay? Put a big square bracket outside. And the NH3 is fine to the power of 4 because you have 4 NH3 there. Okay, so it's the stoichiometry amount. This should have been multiplied. Okay, I don't know why they put a plus there. Okay, they should have checked the infographics. Anyway, there are a lot more covered by transition metal chemistry that I haven't covered within. But my goal in this infographic explanation is to show you the link between the redox topic and the transition metal topics. And not trying to cover every single little bit of the specification of the syllabus. For that, you can go through the topical playlist if you want to. Alright, thank you for watching. I'll see you in the next video. Don't forget to subscribe to the channel. Hit the button below of this video, bottom right, and make sure you share the good contents of the video. On this channel with your friends, your students, if you're a teacher, your colleagues, okay, your whatever group chats that you think might benefit other people, from 14 years old all the way to 18 years old kind of chemistry students, whether they're doing GCSE or O-level or A-level chemistry. Okay, thank you.